Geometric Sequences and Series Part 2. In this video, we're going to look at infinite sequences and series. Really, I'm going to concentrate on infinite geometric series here. So, a couple definitions first. A series, regardless of the type, converges if its infinite sum is finite and unique. Otherwise, the series diverges. So let's explain why these geometric series I'm about to write diverge. Let's start with the series n equals 1 to infinity of 2 to the n minus 1. So if I start plugging in terms, if I plug in n equals 1, I get 2 to the 0, and then plus 2 to the first, plus 2 squared, plus 2 cubed, plus, etc. So if I keep doing this, what happens to the terms in my sequence? Would you agree that my terms are growing without bound? So like 2 to the infinity is going to infinity. So way out at the end of my series or my sequence, I'm doing like 8 plus 16 plus 32, and at the end, plus infinity, plus a bigger infinity, plus infinity, etc. And so if I add all these terms together, don't they quote-unquote equal infinity? Is infinity a finite number? Of course not. So this series diverges because the infinite sum is infinite. I'll just put infinity there. How about this one? What if we have the series n equals 1 to infinity of negative 1 to the n plus 1? What does this equal? Well, again, let's start plugging terms in. When n equals 1, I get negative 1 to the 2. Negative 1 squared is 1. And then n equals 2, we get negative 1 cubed, which is negative 1. N equals 3, we get negative 1 to the 4th, plus 1, minus 1, plus 1, minus 1. So if I add the first two terms together, I get 0. And then if I add the first three terms together, we get 1, and then we get 0, and then 1, and then... So the way out in infinity, what is the sum equal? Well, it's either 0 or 1, both of which are finite. But this series still diverges because the infinite sum, although finite, is not unique. What do I mean by not unique? It's either 0 or 1. Which one is it? I don't know. So we're diverging because we're not hitting a single unique number. Now the question might become, is it even possible to add an infinite number of terms? Is it possible to add an infinite number of positive terms without getting infinity? For example, what if we add 1/2 plus a 4th plus an 8th forever? Now the pattern continues. Do you agree that we're always adding finite terms forever? Positive finite terms. My value, my sum is always getting bigger as I increase my terms. That is, as I increase the number of terms. Is this infinite? Well, let's take a look at an example. It's a very classic example that illustrates these numbers here. Pretend I am in a room, so this is me, and this is the door. To get from my starting place to the door, I have to go halfway. Or you can think of it as being 1/2 a door unit. So now I'm halfway. I'm right there. Now to get to the door, I have to go half of what's remaining. Do you agree that half of what's remaining is 1/4 of the total distance? Half of the half. So now I'm at this new dot. To get to the door, I have to go half of what's remaining. So half of a half of a half. And I could do this forever, right? So 2 questions for you. First of all, if I keep adding these numbers forever, will I be infinite? Well, of course not. Right? Because I'm always going half of what's remaining. So I am going to get some sort of finite value, but here's the bigger question. Do I ever get to the door? So if your answer is no, that means that the first time you went into a room, you never exited it. Well, of course you get to the door. If I keep going forever with this thing, I get exactly 1 door unit away. Okay, you might argue with me. You might say, well, you're not exactly 1 door unit away. You're really close, right? If I keep getting smaller and smaller halves of halves of halves of halves in here, do I ever truly equal 1 when I add all these things together? And my claim is that you do. Now, I will do one thing I will try to do to convince you. What if I had the number 0.999 forever? Which I could write as 0.9 plus 0.09 plus 0.009. And my claim is that this is a geometric series, really, where I have the first term of 0.9, and then I'm multiplying by 1/10 every time to get to the next term. What does this equal? Well, again, my claim is that this equals 1. And you might argue again, it's not 1, it's just really, really, really close to 1. So like I said, I'm going to try to convince you. I'm not going to try to prove it here, but I'm going to try to convince you by doing this problem. What does 0.333 forever equal? And most of you will say it's 1/3. Does it exactly equal 1/3? Well, of course it does. What if I multiply both sides by 3? Then I get exactly 0.999 forever equals 3 times 1/3, or 1. Not close to 1, but exactly 1. And so we have a theorem that we can use when we're dealing with geometric series. In fact, when we're dealing with infinite geometric series. So first of all, if we have a geometric sequence, right, because a series is when we're adding the terms in the sequence. If a geometric sequence has a ratio between -1 and 1, so -1 and 1, which is also sometimes written, or often written, as absolute value of r less than 1, then the infinite sum, and I'll write it with notation, which you might see sometimes, S sub infinity, equals a over 1 minus r. Now, a lot of books put down a sub 1 over 1 minus r. I don't like to do this. I usually write it and say it like this. The infinite sum is the first term in the sequence over 1 minus r, 1 minus the ratio. That's the way I want you to think about it. So let's review. If, and this is a big if, you have a geometric sequence or series where the ratio is between -1 and 1. I've left off a little sign there. The ratio is between -1 and 1. Then the infinite sum is given by first term over 1 minus r. And let's just do a few examples here. Let's do the one we just did, 1/2 plus 1/4 plus an 1/8 plus, etc. So we have a ratio of 1/2, where my ratio is between -1 and 1. It is a ratio. I'm multiplying by 1/2 each time, so I do have a geometric series. That is, I'm adding the terms of a geometric sequence. So I know that the infinite sum is the first term, 1/2, over 1 minus the ratio, which is coincidentally also 1/2. So we get 1/2 over 1/2, which of course is 1. Next example. Let's do the series from 0 to infinity of 2 times -2/3 to the n. Is it geometric? Yep. Because we're multiplying by a common ratio, right? We have the sum of a first term times r to the n, or n minus 1. This is the form of a geometric sequence, and then the summation gives us the series. So I have a geometric series here. My ratio is -2/3, which is between -1 and 1. It is an infinite series, so I can use the formula. The infinite sum is the first term over 1 minus the ratio. So what is the first term? Okay, when n equals 0, the first term of my sequence is 2 times -2/3 to the 0. Order of operations, we do the exponent first. -2/3 to the 0 is 1, so we get 2 times 1, or simply 2. So my first term is 2 over 1 minus the ratio. And the ratio is the thing that's raised to the power. So 1 minus, be careful here, -2/3. So let's simplify this down and be careful. So we have 2 over 1 plus 2/3, right? Which is 2 over 5/3. Now, when you type in a calculator, do it by hand, it's easy to make mistakes. Here's what I do. Notice that 2 is my original numerator, so I'm going to write that as 2 over 1, because I want to make a fraction of both the top and the bottom. And then I put that over 5/3, my original denominator, and that tells me how to flip and multiply it a little bit more easily, giving me an infinite sum of 6/5. Let's do one final problem, sort of like something I showed you above, but we'll do it instead of 0.999, we'll do it as 0.555 forever. And I want to write this as a fraction. How can I write this as a fraction? Well, let's break it down like we did above, as 0.555 forever is 0.5 plus 0.05 plus 0.005, etc. Notice that I do indeed have a geometric sequence added together, making a geometric series, where the first term is 0.5, and then I'm multiplying by 1/10 each time, or 0.1 each time if you want the decimals, to get to the next term. So I do have a geometric series here whose ratio is between -1 and 1, which means that the infinite sum is the first term, and I'll put that down as 5/10, you'll see why in just a bit, over 1 minus the ratio, 1 minus 1/10, giving me 5/10 over 9/10, which equals 5/9. So 0.555 forever can be written as 5/9.